Okay, the dreaded resolution question, right? So we know that the wavelength over the difference in wavelength we can resolve is the order times the number of lines that are illuminated, right? And so we know that the lambda is going to be 428, right? So we know that. This is what we're trying to solve for. Let's see, first order, that makes the sky 1, right? Smallest. Okay, so now we got to figure out how many lines are illuminated, right? And this gets tricky. Okay. Now in the previous problem, we figured out that the distance between these guys is 1.370869 times 10 to the minus 5th meters, right? Okay. So if the beam is 1.6 millimeters wide, then n is going to be 1.6 times 10 to the minus 3rd meters, right? Divided by, that's the meters in the beam, right? Divided by 1.370869 times 10 to the minus 5th meters. I don't know how to explain that. I guess this is the width of the beam, right? And this is how wide each of the slits are. So the question is, how many of those fit into the width of the beam, right? That's the question, right? I guess that makes sense. Okay, so 1.6 times 10 to the minus 3rd. That's 1.6 millimeters, right? Divided by that very small number that I got there. This isn't going to be a huge number, right? This is 116.7 lines. Okay? So now we're set. Now we can set this thing up. So we got 428 divided by the thing we're trying to solve for, right, is equal to 1. It's the first order, right? Times n is 116.714, et cetera, right? All right, so I guess it's 428 divided by this. So I'm going to go 428 divided by the number I just got. And I get that the difference in wavelength is kind of big that we can resolve. Okay, this isn't good, right? You want this to be small, that we can resolve very small differences. But we can only resolve it's 3.667. So it's about 3.67 nanometers. And that's because, I guess our diffraction grating is a really good diffraction grating has thousands of lines, and this one's only 729 lines per centimeter. So anyway, yeah, there you go.